So,
yes, this is the next page.
okay.
Oh, okay.
So, because we don't have the interval between the next and next talk, so if there is Yuaki-san, please check the sharing.
Okay. Can I share? Can I share my slide?
Yeah, yes, now I can see.
Okay.
But it not in the full screen.
Presentation.
Okay.
Is, yeah.
Yeah, it's
Next
good.
slide. Okay.
Okay, thank you.
Thank you.
So, okay, thank you. Okay, so shall we start the third talk? The next talk will be given by Shumpei Iino from the ISSB University of Tokyo, and he's going to tell us about the extracting boundary CFT data from lattice model with tensor network renormalization. So please, Iino-san.
Okay, thanks for the introduction, Okubo-san. I'm Shumpei Iino, a PhD course student working in ISSP, University of Tokyo. First of all, I'd like to thank the organizers for inviting me such a nice workshop. Okay, let me begin my talk with introducing BCFT, or which is short for boundary CFT. As its name suggests, BCFT is just a conformal field theory in geometry with open boundary, such as finite cylinder or semi-infinite plane geometry. And in fact, BCFT is very important in various regions of physics. For example, in high energy physics, BCFT is essential to study deep brain and ADS BCFT, as is discussed in this workshop. On the other hand, in condensed matter physics, Kondo problem or surface critical phenomena, this is my research interest. These were traditionally important application of BCFT. So especially in condensed matter physics, the lattice model is very important due to its cross connection to realistic material. And the interesting thing in lattice model is that the emergence of conformal invariance at the critical point. So this is a highly non-trivial phenomena. So I would like to discuss the how to study the emergent BCFT on lattice models numerically. And I would like to focus on the two-dimensional lattice models. So our purpose is the extracting the BCFT data from given critical lattice models with open boundary. And BCFT is emergent as a low energy physics. So we would like to use RG technique. And as this RG technique, we would like to introduce the tensor renormalization group, TRG method, which is briefly commented in the Okubo-san's talk. This method is known as an accurate method to study conformal field theory on lattice models. However, this model was originally proposed for the periodic boundary condition case, but we are now interested in the BCFT, so I extended this method to open boundary systems. And finally, I'd like to briefly introduce the simplest but non-trivial application of a method to surface critical phenomena. Okay, let me begin my first part of my talk. Before discussing the tensor renormalization group, we need to introduce tensor network representation. Actually, many things in many-body physics can be represented in tensor network. For example, Euclidean path integral of a 1D quantum model and the partition function of a 2D classical model can be represented as the contraction of the tensors placed on 2D space, like this. And as another example, the wave function of 2D quantum systems called PEPS ansatz is also the 2D tensor network. I think some of you may not be familiar with this kind of tensor network representation, but the important thing is that in each local tensor, the information of local degrees of freedom are all implemented, such as the interaction between spins or particles or something like that. So the natural question is, how can we extract the many-body information from each local tensor? And one of the methods to do to study this kind of thing is tensor renormalization group, TRG. TRG is the in some sense, Kazanov real space renormalization group on tensor network like this equation. Okay, let's suppose we have a tensor net, this small tensor network with 4 tensors, and consider replacing this tensor network as some single tensor T prime by using some approximation. This is kind of a real space renormalization group, right? So using this RG procedure, we can coarse-grain the tensor network from this to some large-scale tensor network like this. And very interestingly, if we repeating this RG procedure, the local tensor converges to some fixed point tensor, similarly to the Wilsonian and Kadanov's renormalization group. And from this fixed point tensor, we can extract the many-body information of the system. For example, if the system is in trivial phase, the fixed point tensor becomes also trivial, where only one element is finite and all other elements are zero. And if the system is at the critical point, the fixed point tensor becomes infinite dimensional tensor from which one can extract the information of conformal field theory. Okay, so the problem is concretely how to perform this approximation numerically. Yeah, actually, there have been so many algorithms to do this, but today I'd like to briefly introduce one famous algorithm called tensor network renormalization, TNR, which was proposed by Nevenbrin and Vidal. Okay, what we want to do is renormalize this tensor network to some single tensor T prime. And to do so in this TNR, we need to insert some a little complex tensor networks like the figure. But the point of this algorithm is this green tensor U. Yeah, in fact, this rank 4 tensor plays the same role in disentangler in Mera, which is also proposed by Vidal. The disentangler is very important to eliminate short correlation in this tensor network, which represents the quantum critical wave function. Yeah, in fact, this TNR algorithm generates Mera in some sense. So let's suppose that applying TNR procedure to this tensor network geometry, and after two-step renormalization, TNR renormalization, we have this tensor network. And here and here, the mirror network up here. Yeah. Anyway, what I want to tell you is that because TNR is really closely related to mirror, so TNR can also efficiently deal with critical systems. Yeah, in fact, I'd like to demonstrate that we can extract a CFT spectrum from a fixed point tensor using TNR. Okay, first of all, let's consider the partition function on this n times m torus geometry. And in ranges of tensor network, the partition function can be represented like this equation. This is a transfer matrix constructed from the local tensors. On the other hand, the partition function can also be represented in this equation. This part is the universal part from conformal field theory, where L0 is the dilatation operator in Virastor algebra, and C is the central charge, and F is the free energy density. So comparing these two equations, we can see that the scaling dimensions and the central charge can be calculated from the eigenvalue spectrum of this transfer matrix, like this equation. Yeah, in fact, this is the numerical results of the 2D critical classical Ising model on lattice. And the cross mark represents the numerical constructed spectrum, and the green circle represents the exact scaling dimension of 2D Ising CFT. So as you can see, the numerical results are very accurate and accurately consistent with the CFT spectrum. And as another application, I'd like to demonstrate that TNR can also deal with the PEPS wave function. Okay, let's consider the PEPS wave function constructed from this local tensor. This is an 8-leg tensor where alpha, beta, gamma, delta are virtual bonds, and I, J, K, L represents the physical bonds. And the element of this local tensor is parameterized like this equation by using some continuous parameter G. Yeah, actually, it is known that the PEPS wave function of this local tensor represents the toric wave function when G is equal to 1. On the other hand, when G is equal to 0, this wave function represents the topologically trivial phase. So we have a topological phase transition between the two phases at this point. Now, if we perform the TNR renormalization of Pep's wave function at this critical point, we can extract we can obtain this conformal spectrum. A red plot represents the numerically constructed spectrum, and this is a central charge. Because central charge is very close to 0.5, and scaling dimensions are very consistent with the 2D Ising CFT. So we can see that this topological phase transition falls into Ising universality class. Yeah, actually, it is very difficult to calculate the critical exponent from order parameter in topological phase transition. So this kind of method is very powerful if you want to study the critical phenomena in topological phase transition. Okay, let me go into my original work part. Okay, please remember that we were interested in the boundary CFT, but the TNR was proposed for periodic boundary case, so we needed to generalize TNR for open boundary systems. Okay, here, let's consider the finite cylinder geometry for simplicity. And the tensor network on this geometry can be represented as three types of tensors like this. One is the bulk rank for tensor T, and the other are the boundary tensor, rank 3 boundary tensor, TS1 and TS2. And we can consider the renormalization on this geometry, on this tensor network, and which can be decomposed into two parts. First part is the ordinary bulk renormalization. And actually, this is exactly the same as the ordinary tensor network renormalization. And the second part is renormalization for boundary tensors from this tensor network to this single boundary tensor. Yeah, although I don't discuss the detailed algorithms today, but we can easily design the algorithm so that the proposed algorithms can generate the boundary mirror similarly to the periodic boundary case. So if we apply the proposed algorithms to this tensor network, after two steps, we can have this tensor network under here. We can see that the boundary mirror appear. So maybe you can easily imagine that this tensor network algorithm, TNR algorithms can also deal with the critical system with open boundary. Okay, I'd like to explain how to extract the BCFT spectrum, but the strategy is almost the same as the periodic boundary case. The partition function on this n times m finite cylinder geometry can be represented as this equation using a tensor network. This is the transfer matrix. On the other hand, this is another representation of the partition function. This part is the universal part from BCFT, and this is the free energy density, and this is a surface free energy density. And this is the so-called boundary entropy or Affleck-Ludwig's entropy. So comparing these two equations, we can see that the scaling dimension and the central charge can be calculated from the eigenvalue spectrum of this transfer matrix. Okay, before showing the numerical results, I'd like to notice that the one interesting feature of BCFT is that the operator spectrum depends on what boundary condition we imposed. For example, in the ordinary periodic boundary case, that there are three primary operators in operator spectrum: identity, energy, and spin operator. But if in boundary CFT case, if we impose the free boundary condition on both sides of the finite cylinder, the operator spectrum consists of only identity and epsilon operator. So there is no spin operator. And furthermore, if we impose the ordered boundary condition, the operator spectrum is just the identity operator. But our methods can successfully detect this difference. This is a numerically constructed spectrum. The red plots is a numerical result, and this is a free boundary condition case, and this is a ordered boundary condition case. Yeah, the numerically constructed spectrum are accurately consistent with the BCFT conjecture. So our methods are also works well for boundary CFT case. Okay, finally, I would like to briefly introduce the application to the surface critical phenomena. Okay, today I would like to introduce the surface critical phenomenon of so-called tricritical Ising model. I don't know whether the people in high energy and quantum information are familiar with this model, but just in case, let me explain this model. So this is the Hamiltonian in question, which is called the 2D classical dilute Ising model. And the sigma is the just Ising spin, but this spin can take also 0 in addition to -1 and +1. And the first term is just the ordinary Ising interaction. The second term, D term, suppresses the appearance of this spin 0. And one interesting feature of this model is that if we fine-tuning the parameter K and D, we can have another universality class than Ising CFT. At this point, the critical phenomena corresponds to the CFT, whose central charge is 7/10, a so-called tricritical Ising point. At this tricritical point, we can observe an interesting surface critical behavior. Okay, first of all, it is widely known that there is no phase transition, no phase transition at finite temperature in 1D classical systems, which is also called Pyre's argument. So the 1D classical system is not interesting, but let's consider the 1D classical systems attached to 2D bulk. In other words, let's consider the 1D classical edge in the some 2D classical systems. And in that case, if we fine tune the bulk at the tricritical point, this 1D classical edge can exhibit the spontaneous symmetry breaking at finite temperature. Yeah, which is proposed by Affleck. So let me explain this phenomena using the lattice model. Okay, as I said, we fine-tune the parameter K and D at tricritical Ising point. And the control parameter here is this Ks, which is the interaction on the spins living in edges. So, and if Ks is very small, the boundary is disordered, namely free boundary condition. But if Ks is very large, the boundary is ordered. And we can have a phase transition between the phases at finite Ks. So this phenomena can tell us that the 1D classical chain is not interesting, but the 1D classical surface can be interesting. And I'd like to notice that more complex surface critical phenomena can appear in higher dimensions. Yeah, anyway, let's go back to the tricritical Ising case. Yeah, in fact, this phenomena was conjectured by boundary CFT argument by Affleck. Oops. Yeah, according to that argument, this free boundary fixed point and ordered boundary fixed point are stable fixed point because this fixed point has no relevant operator. Yeah, according to the BCFT analysis, the most relevant steering operator is this epsilon double prime, whose steering dimension is 3/2. But because 3/2 is larger than the spatial dimension 1, here we are considering the 1D classical edge, so spatial dimension is 1. So this steering operator is irrelevant, and also this is irrelevant. So that's why these two fixed points are stable. On the other hand, at this transition point, there are two relevant scaling operators, 1/10 and 3/5. Yeah, but this is just a BCFT conjecture. So I performed a numerical TNR calculation and calculated the conformal spectrum like this, and the results are completely consistent and very accurate. So the bottom line is that the TNR method can be very helpful if you study the surface critical phenomena with respect to boundary CFT. Okay, let me conclude my talk. I introduced the tensor network renormalization algorithms, which a numerical algorithm inspired by Miller. And using this algorithm, we can efficiently extract the 2D CFT data from the 2D tensor network, like this. This network. And I extended the TNR method for open boundary systems, and the proposed algorithm works well also. And we can accurately extract the BCFT spectrum from lattice models. And actually, there are some interesting future issues. For example, I'm interested in how to extract other BCFT data, such as OPE coefficients of boundary and bulk boundary. Actually, fixed point tensor should have this kind of information. So in principle, we can extract this information, but I don't know how. Okay, now it's time. So that's all. Let's. Okay, thank you for your kind attention.
Thank you very much. So, the audience, do you have any questions or comment? So, if you have, please raise your hand. Can I ask a naive question?
Okay.
I'm interested in your argument, Affleck's argument, so that the H 1D system can have the phase transition.
Mm-hmm.
So I naively feel that it is due to the long range interaction through the bulk. And so if the bulk is not critical, is it possible to have the phase transition at the edge?
Yeah, I think it's impossible because if the when bulk is at critical, the correlation length is divergent. So the this is not isolated. Not in this sense, this is not 1D classical systems. But if the bulk is not of bulk is off critical, the correlation length is finite. So this bulk is in this sense just isolated edge.
Okay.
So
Thank you. And so it means in order to observe the edge phase transition, we need to tune the parameter.
All right. And it is known that if the bulk is just Ising criticality, there is no finite edge phase transition.
Okay. Thank you very much. So Takayanagi-san, please.
Thank you very much. I'm very curious about this tensor network structure in the presence of boundary. And so can you compute the boundary entropy in your analysis? And if so, so changing boundary entropy corresponds to what kind of aspects of tensor network?
Sorry. Okay. The boundary. Yeah. In principle, maybe. We can calculate the boundary entropy from tensor network analysis by using some finite size scaling analysis. And sorry, could you ask again the second question?
Second question is that if we compare the situation where boundary entropy is very large or very small, does it affect the structure of tensor network? I thought the more expression. What I mean is just so nearby boundary region. So you have many tensors.
Yes.
And so this number of tensors is the same, even if you change the boundary condition.
Yes. The same. It doesn't depend on the boundary condition.
But on the other hand, we can roughly estimate entanglement entropy. And if number of tensors is the same, so that rough estimation, we get the same result.
Okay. Yeah.
So, but if we have because boundary entropy contributes also to entanglement entropy. So I expect maybe there are some extra tensors, which gives extra contribution to entanglement entropy. But maybe this formalism is maybe not like this. I think probably.
I think the Takayanagi-san's discussion is based on the assumption that the bond dimension is the same.
Yes.
Okay, but so in this method, we can tune the bond dimension. We fix the tensor network structure.
Right. I see.
I see. If we rewrite everything in the same bond dimension, like tensor, maybe they're extra. Tensor,
maybe. Yes, maybe so.
But I thank you very much. Yeah, I understand that.
Yeah, thank you for your question.
Any other questions? Kunishi-san, please.
Yes, so you didn't mention about the details of the boundary TNR. So, but yes.
Maybe yes, this is a supplementary.
Yeah, and
slide
for example, the left side figure, you have always single layer boundary tensor.
Right.
But in actual situation, the boundary effect penetrate into the bulk region with the power law, I think.
Yes.
How can you take into account such a power law behavior by using only single site boundary tensors?
Yeah, I think that's would be difficult, and the same problem happens for the boundary mirror. So we need to some we need some assumption that the boundary effect can be does not expand to bulk part with some exponentially larger speed.
So in the bulk region, maybe the orange color tensor is basically uniform in the bulk region. Is this right?
Yes, I'm now assuming that.
I see. Okay, thank you.
Okay, so time is up. Thank you, Iino-san.
Okay, thank you.
The next, Iwaki-san, please share your screen.
Okay. Can you